A racetrack is constructed such that two arcs of radius 80 meter at A and 40 meter at B are joined by two stretches of straight tracks, as in the figure. In a particular terrain, a driver traveled a constant speed of 50 meters per second for one complete lap. In this case, the ratio of the tangential acceleration at A to that at B is. Here we are talking about tangential acceleration. Okay? Since the speed is constant, this is tangential speed. There is no change in the tangential speed. Therefore, there will be a change in the tangential acceleration. You need to change the magnitude of the speed to change the magnitude of tangential acceleration. So the tangential acceleration is 0 at both points. How about the centripetal acceleration? For centripetal acceleration, we know that it depends on the value of r, right? It's v squared over r, v squared over r. So r here is half r there. Therefore, the acceleration here will be double the acceleration there. Okay? A centripetal is v squared over r. Okay? So smaller r means bigger acceleration. Bigger r means small acceleration because v, the magnitude of the velocity, is constant in this problem. An object moves in a circular path with constant speed v. Which of the following statement is true concerning the object? Its velocity is constant, but its acceleration is changing. Its acceleration is constant, but its velocity is changing. Both its velocity and acceleration are changing. Its velocity and acceleration remain constant. Okay. As a rule of thumb, wherever there is circular motion, the velocity will be changing direction. Therefore, it is not constant. Changing direction for the velocity means there will always be acceleration, because wherever the velocity changes, there will be acceleration. So this is the right answer. Both the velocity and acceleration are changing. Although the speed is constant in magnitude, but because of the change in direction, we will have the velocity and accelerations changing. Example: a race car accelerates uniformly from a speed of 40 meters per second to a speed of 60 meters per second in 5 seconds, while traveling counterclockwise around a circular track of radius 430 meters. When the car reaches a speed of 50 meters per second, calculate the magnitude of the car's centripetal acceleration. You have circular motion, so yes, there should be centripetal acceleration, the angular velocity, the tangential acceleration, and the total acceleration. Again, this example is just to sharpen our skills regard to the new variables of motion that we learned about. So for the centripetal acceleration, straightforward, just use this equation, v squared over r. Always, v squared over r will give you the centripetal acceleration. V is 50 meters per second, square it, divide by the radius r. Okay, so you have the answer for the centripetal acceleration. Then for the angular velocity, it's v over r, v divided by r. So r, the radius is 400, not 430. There is a typo here that we need to pay attention. So this should be 400, not 430. Okay, for the radius. Then the magnitude of tangential acceleration. Tangential acceleration is the change in the speed divided by the change in time. 60 minus 40 divided by the elapsed time. So it's 4 meters per second squared. And the total acceleration square root of AT squared plus AC squared. We evaluate that it is 7.42 meters per second squared. In general, wherever you have an object in a circular motion, there should be a centripetal force to force it to move along this trajectory. Like when a planet rotates around the sun, the gravitational attraction, that is the force, that is the centripetal force, keeps the planets in orbit. Okay? So we will always need some force to keep the object in its circular trajectory. This force is an external force. It is external to the object. Okay? And if you consider, like for example, a ball whirling in a circle here at the end of a string, the force is going to be the tension force in the string. For a planet, it's the gravitational force. Okay? So keep in mind this. If you have a car moving on a flat circular track, the centripetal force is generated from the friction between the tires and the track. So if you recall in Newton's second law of motion, force equals mass by acceleration. So the centripetal motion, Fc equals MAC, AC for centripetal, which is V squared over R. That is the value for the centripetal acceleration. So any circular motion will have a centripetal force that can be expressed by this equation, mv squared over R, because the centripetal acceleration is V squared over R. This is an important equation. This is in Newton's law for circular motion. We just substitute for the acceleration V squared over R. All vectors will have direction. Force is a vector, as we know. So the force vector will have a direction. If the force is directed toward the center, it would be negative. Just like a satellite in orbit, the gravity force downward, that would be negative. On the other hand, if the force is away from the center, the direction of the force will be positive, like the normal force on a car traveling over a circular crest of a hill, or the force of repulsion between like electric charges, that would be positive. By the same language, centripetal acceleration is negative because it acts toward the center. The direction of centripetal acceleration is always toward the center, so you can give it a negative sign, just like we do with G for free fall. G for free fall, it's always falling toward the center of Earth, and because of that, we give it the minus sign. It's minus 9.8 meters per second squared. The same convention. So when you apply in Newton's second law, if you are talking about centripetal force, you have a minus sign for the acceleration. It is falling toward the center. If it is away from the center, then it would be a positive sign. When it is away from the center, we call that centrifugal force. Centrifugal force. So you have centripetal and you have centrifugal. Centripetal has a minus sign. It is directed toward the center. Centrifugal is directed away from the center, and it is assigned a positive sign. When you solve problems as Swiss, it's helpful to sketch the free body diagram to define the coordinate system, decide which direction is positive, which direction is negative. Then find the net external force. In this case, for rotational motion, the net external force is going to be centripetal force. You need centripetal acceleration to keep the object in orbit and rotation. And then apply in Newton's second law, force equals mass by acceleration. You may have two components for the force vector, tangential and radial. For tangential, it is MA tangential. For radial or centripetal, it is MA centripetal. And A centripetal is equal to V tangential squared divided by R. These are important formulas that you need to keep in mind when you solve problems. Example: a car travels at a constant speed of 30 miles per hour. When you convert, this is equivalent to 13.4 meters per second. So this travels at constant speed on a level circular turn of radius 50 meters, as shown in the bird's eye view in figure A here. What minimum coefficient of static friction MUS between the tires and roadway will allow the car to make the circular turn without sliding? This is an important piece of information that we are learning about. So the thing that allows us to rotate when you have a circular road or street is friction. Without friction, we will not be able to do this kind of rotational motion. So the static friction, because the car is not moving this direction, the car is moving in the perpendicular direction. So the friction that is of interest to us is static friction. There is no motion along this direction for the tire. The motion is forward or backward. Okay. So static friction is the centripetal force here that allows the car to rotate. As always, we have mg, the weight of the car, and we have the normal force going upward. So now we know the source of the centripetal force. The centripetal force is just the force of friction, and the force of friction is just MUSN, as we know when we studied friction. You need the normal force multiplied by the coefficient of static friction. This is your centripetal force. Since there is no motion along the vertical direction, so N minus mg equals 0. N minus mg equals 0. There is no motion along this direction. Okay, the net force for the y-axis, N minus mg equals mass by acceleration. There is no acceleration, so that is 0. Therefore, N is just mg. The normal force is just mg. So you substitute here for N, it is mg multiplied by the coefficient of static friction. This is equal to the centripetal force, which is mass by centripetal acceleration, v squared over r. We cancel m with m here, and now we can solve for mus. Mus, the coefficient of static friction is v squared over rg. V squared over rg. Okay, when you plug in the numerical values for v, 13.4 meters per second, and for r it is 50 meters, and g 9.8 meters per second square. Evaluate. So the coefficient of static friction is 0.366. Okay, this is the coefficient of static friction needed to maintain this motion, friction between the tires and the road. Another example, The Daytona International Speedway in Daytona Beach, Florida is famous for its races, especially the Daytona 500 held every February. Both of its courses feature four-story 31-degree banked curves with maximum radius of 316 meters. If a car negotiates the curve too slowly, it tends to slip down the incline of the turn, whereas if it's going too fast, it may begin to slide up the incline. Find the necessary centripetal acceleration on this banked curve so the car won't tend to slip down or slide up the incline. Neglect friction. Calculate the speed of the race car. So now, because of banking of the road, we will get the centripetal force. If you study the free body diagram, you have the weight going downward, mg. You have the normal. The normal is always perpendicular to the surface. So this is the normal. The normal makes an angle theta, which is the same angle of banking for the road here. Okay? We can decompose the normal force into two components, one vertical and the other horizontal. The vertical component will balance mg downward, and the horizontal component will generate needed centripetal force. Okay, so the total forces, the net external force, is just the normal force and the weight, because we are told ignore friction for this situation. We don't need to worry about friction. So you have just these two forces, N and mg. To simplify this, we decompose N into vertical and horizontal components. Then for the vertical equation, since there is no motion along the vertical axis, so you have N cosine theta minus mg equals 0. Therefore, N is mg divided by cosine theta. Then for the horizontal component, this is the centripetal force. Centripetal force, there is no other force along the horizontal direction. So it is minus N sine theta. Okay, we substitute for N, mg over cosine theta. Mg over cosine theta, this is for N, multiplied by sine theta. So you end up with minus mg tan theta. Okay, this is the centripetal force. We are good. Once you know the centripetal force, you can calculate the centripetal acceleration from a Newton's second law, MAC equals FC. So AC is FC divided by M. If C is minus mg tan theta, we divide that by M. M cancels with M, and we ended up with this nice but important result, minus g tan theta. Okay? So the centripetal acceleration, as you can see here, depends on the banking angle. Okay, the angle here will determine what kind of centripetal acceleration we may have. Substitute, we are told in the problem that the banking angle is 31 degrees. So substitute for theta 31 degrees, for G 9.8, evaluate. It is 5.89 meter per second square, and the minus sign is just to tell us it is centripetal. It is toward the center. Okay. Then we know that the centripetal acceleration is v squared over r. So now we can solve v. V here is the tangential velocity. V is the square root of minus r multiplied by AC minus the radius we are told is 316 meter and AC is minus 5.89. Evaluate, this is 43.1 meter per second square. No, it's meter per second. Another type here, sorry. So it's 43.1 meter per second. So if the car moves with this velocity, it will maintain its motion in the orbit. If it speeds up, then it will slide up. If it speeds down, then it will move down, it will slide down. Okay, so the driver needs to keep this velocity if he or she wants to keep the same path for the car.